Scientists just discovered compact red lights in the early universe that may not be ordinary galaxies at all. In the year 12,043, the Future Archives catalogued the Ember Crown, a heat-scarred navigation halo whose inner rim was burned by a source brighter on one side than the other, as if something dark at the center was doing the shining. If that reading is right, the mystery is no longer just what JWST saw, but whether some of the first stars were really black holes wearing stars as camouflage. The Ember Crown was not built for a normal sun. Its surviving veins are scorched in one quadrant, not evenly all the way around. The shutter mounts carry repeated warning marks around a dark center. 2 approach cones are etched as safe. A broad plane is marked forbidden. That geometry matters. Ordinary stars radiate from a surface. Dangerous, yes, but roughly spherical. This object records something else, a source with direction, a source with a hidden core, a source whose brightest emission likely came from a disk, jet, or reprocessing shell, rather than from fusion across a stellar photosphere. That alone does not prove a black hole star. It only eliminates the simplest explanation. Then came the older evidence. In the early 21st century, the James Webb Space Telescope began finding compact crimson points in the young universe. Objects so red, so concentrated, and in some cases so luminous that astronomers could not agree on what they were seeing. They became known, informally, as little red dots. Some turned out to look like obscured active black holes. Some may have been unusual early galaxies, and some opened a more unsettling possibility, that the first bright objects after cosmic dawn may have included things that looked star-like from the outside, while their true power source sat in darkness at the center. To understand why these red points cause such trouble, start with a simple rule. A black hole is dark. The gas falling into it is not. Matter spiraling inward can release energy with an efficiency far beyond ordinary stellar fusion. Fusion turns a small fraction of mass into energy. Accretion onto a black hole can do better, because gravity converts infall into heat and radiation with brutal effectiveness. In the right circumstances, a feeding black hole can outshine an entire galaxy. So, the scientific question is not whether black holes can become luminous. We know they can. The real question is whether a black hole can hide inside a giant envelope of gas and inflate that envelope into something that behaves, from a distance, almost like a star. That is the modern quasistar idea. A black hole buried inside a massive gaseous shroud. The core does not shine directly into space. Its radiation is trapped, scattered, and reprocessed by surrounding gas. What escapes may look cooler, redder, and larger than the violence at the center would suggest. This is established theory in the narrow sense that the model exists in peer-reviewed astrophysics. It is not established in nature. No confirmed quasistar has ever been observed, which makes JWST's little red dots so important. Because if even a fraction of them are real black hole stars, they could explain how the early universe built giant black holes far faster than our simplest growth models allow. Here is the growth problem in plain terms. By the time the universe was less than 1 billion years old, astronomers were already seeing quasars powered by black holes with masses of roughly 1 billion suns. That is not controversial. Those objects are real. The controversy is how they got so big so fast. If the first black holes began as ordinary stellar remnants, perhaps tens of solar masses left behind by the deaths of the first stars, then they had very little time to grow, and black holes do not simply swallow everything around them without limit. Radiation from the infalling gas pushes back. That limit is often described through the Eddington balance. Gravity pulls matter in, radiation pressure pushes outward. Feed too aggressively, and the system can blow material away instead of gaining it. This is one of the most useful facts in the whole debate. Black hole growth is not set only by appetite. It is set by feedback. So when JWST and earlier surveys reveal very massive black holes in the young cosmos, astronomers face 2 broad options. Either those black holes started heavier than expected, or they found a way to grow under conditions that evade the naive limit. Quasistars are attractive because they may offer both. They begin with a heavy, gas-rich environment, and the thick envelope can trap radiation long enough for the central black hole to gain mass rapidly before the whole structure tears itself apart. In other words, the envelope is not decoration. It may be the cheat code. The notion has older roots than the Webb era. As far back as 1963, Fred Hoyle and William Fowler were already considering whether extremely massive stars might be powered in part by compact energy sources deep inside them. The modern quasistar model was formalized much later, in 2008, when Mitchell Beagelman, Elena Rossi, and Philip Armitage described a black hole embedded inside a massive, radiation-supported envelope. The elegance of the model is easy to miss. A naked accreting black hole radiates straight into its surroundings and can choke off its own fuel supply. But bury that engine inside enough gas and the escaping energy is delayed, thermalized, and redistributed. The outside of the object may settle into a swollen, cooler-looking photosphere even while the center is violently feeding a black hole. That distinction matters because telescopes do not see engines. They see processed light, and processed light can lie. A compact source wrapped in thick gas may look red, not because it is cold in the ordinary stellar sense, but because hotter radiation has been absorbed and re-emitted at longer wavelengths. In the early universe, where Webb observes heavily redshifted infrared light, that ambiguity becomes even worse. So, when astronomers look at a little red dot, they are not asking one question. They are asking several at once. What produced the light? What reprocessed it? And how much of the object is hidden from view? The phrase little red dots sounds almost trivial. The data are not. JWST revealed a population of compact red, high redshift sources that often look too concentrated to be normal extended galaxies. In some cases, spectra showed broad emission lines, a classic sign that gas may be moving rapidly around a central massive object. Some analyses argued that many of these sources are best explained as dust-obscured active galactic nuclei, black holes already feeding in the centers of young galaxies. That is a major result even without quasistars. It would mean black hole growth switched on extraordinarily early. But another layer of uncertainty remains. Broad lines can be interpreted in different ways. Dust changes colors, geometry changes brightness. Unresolved structure blends host galaxy light with nuclear emission. And if the object is seen through a thick envelope, the radiation that reaches us may be a distorted summary of something more extreme underneath. This is why no single spectral signature has settled the debate across the whole population. There may not be one answer for all little red dots. Some could be ordinary dusty galaxies. Some could be hidden AGN. A smaller subset might represent direct collapse systems or quasi-star-like states. That mixed population possibility is often less dramatic than a single grand explanation, and more realistic, because nature rarely arranges its evidence into one neat category. For a black hole star to exist, several difficult conditions must line up at once. First, enormous amounts of gas must fall inward without fragmenting into ordinary stars too early. That usually means a very special environment, metal-poor gas, limited cooling, and often a strong ultraviolet background that suppresses molecular hydrogen, the coolant that helps clouds break apart. Second, angular momentum has to be removed. Gas does not like falling straight inward. It wants to orbit, unless turbulence, gravitational torques, or instabilities can move that angular momentum outward. The collapse stalls. Third, feedback has to be balanced with exquisite precision. Too little radiation trapping, and the inflow is blown apart. Too much trapping, and the envelope may become unstable, pulse, or shed mass catastrophically. So, the challenge is not merely to make a black hole inside gas. The challenge is to make a black hole inside gas that stays inflated long enough to matter. This is why theorists argue over lifetimes. A quasistar that survives for a meaningful interval could grow a seed black hole to 10,000 or even 100,000 solar masses. A quasistar that lasts only briefly may still exist in principle, but become almost impossible to catch in the act. That matters for the observations. A rare object can be real and still fail to explain an abundant signal. If you've enjoyed this investigation so far, subscribe to future archives. There's another mystery on the way. The strongest conservative interpretation is not that Webb found a new class of object. It is that Webb found familiar physics in an unfamiliar regime. Early galaxies were dense, compact, chaotic, and likely rich in obscuring material. If a growing black hole sits inside one of those systems, its light can be reddened by dust, broadened by fast-moving gas, and misread because the galaxy is unresolved at extreme distance. Small errors in line interpretation or geometry can produce large errors in inferred black hole mass. That is not a loophole. It is standard observational caution, and it has force behind it. Several recent analyses argue that many little red dots are best understood as obscured AGN, rather than pristine exotic objects. In that picture, the universe did not need black hole stars to generate the signal. It only needed us to underestimate how strange ordinary early galactic nuclei can look. This pathway preserves most of conventional galaxy evolution. Black holes still grow early. Heavy seeds may still exist. But the red dots themselves do not become evidence for quasistars. Notice what this explanation does well. It uses phenomena already observed nearby: accretion disks, dust reddening, broadline regions, orientation effects. Its weakness is different. If future spectroscopy keeps finding black holes that seem overmassive for their hosts, then ordinary obscuration may stop being enough. The conservative model survives by fitting the data better than the exotic one, not by sounding safer. The more radical interpretation keeps the observations and changes the engine. In this view, at least some little red dots are not ordinary galaxies with hidden nuclei. They are transitional objects from cosmic dawn, heavy black hole seeds wrapped in thick envelopes, glowing mainly through reprocessed accretion light. That would solve several problems at once. It would help explain how the first supermassive black holes gained a huge head start. It would make sense of sources that appear too compact and too energetically peculiar for simple stellar populations. And it would force a useful correction on our intuition. Not every star-like light in the early universe had to be powered mainly by fusion. But this scenario pays a high price in physics. The environmental window may be narrow, inflow rates must be extreme, fragmentation has to stay suppressed. The envelope has to survive feedback long enough to regulate, not simply explode. And even if all of that happens, the object may be brief. That produces a third possibility between the two camps. Black hole stars may have existed, but only as violent, short-lived failures, real enough to shape black hole demographics, too fleeting to dominate Webb's census. By this point, the Ember Crown begins to look less like proof of one answer than a warning about the entire question. The source it faced was not merely bright, it was directional, unstable, and hidden at the center. Exactly the kind of evidence that keeps all three explanations alive. If black hole stars were real, the next question is not whether the idea is beautiful. It is what evidence would actually separate one from a dusty active galaxy. That standard matters because astronomy is full of imposters. The universe often hides one engine behind another. Dust can cool a spectrum. Geometry can narrow or broaden lines. A compact, unresolved galaxy can look simpler than it is. And an accreting black hole buried in gas can masquerade as starlight if its radiation is absorbed and re-emitted at longer wavelengths. So, what would observers look for? First, a mismatch between the apparent size, color, and power source. A quasistar-like object should look swollen and relatively cool on the outside, while the real energy comes from deep inside, where gas falls toward a black hole. That means the emitted light is not tracing a normal stellar surface in thermal equilibrium. It is tracing reprocessed accretion. Second, unusual line behavior. Broad emission lines can come from ordinary active galactic nuclei, so broad lines alone prove very little. What matters is the combination of line width, line ratios, continuum shape, and inferred black hole mass compared with the mass of the host. Third, statistics. A theoretical object may fit one spectacular source and still fail as an explanation for a whole population. If little red dots are common, then the mechanism creating them cannot live in only an absurdly narrow corner of cosmic conditions. That is one of the most useful scientific habits in this entire case. Never ask only whether a thing can exist. Ask whether it can exist often enough. This is where the argument becomes sharper. Some early sources do not merely look red. They appear to host black holes that are unexpectedly massive compared with the galaxies around them. That comparison is powerful because in the nearby universe, black hole mass and galaxy properties are not random. There are correlations between central black holes and the bulges of their host galaxies. They are messy and they evolved over time, but they give astronomers a baseline expectation. The host and the hole usually grow in some relationship to one another. In parts of the early JWST record, that relationship may be disturbed. If the inferred black hole is too massive for the visible host, several explanations open up. One is measurement bias. Virial mass estimates rely on assumptions about gas motion, geometry, and line interpretation. If the broad line region is viewed at an awkward angle, or if extinction hides part of the source, the black hole mass can be pushed upward. Another explanation is that the host galaxy itself is underestimated. Faint extended starlight is hard to recover at high redshift. A compact, brilliant center can drown the surrounding system. And then there is the more disruptive possibility: the black hole really did form first, or at least grow first. That is exactly the kind of universe in which heavy seeds matter, not because they are exotic for the sake of being exotic, but because they change the timetable. Start with a seed of 100 solar masses, and the growth race is brutal. Start with 10,000 or 100,000, and the first quasars become much easier to understand. A black hole star is one proposed machine for creating that head start. The timing problem is easy to state and hard to solve. We know quasars with black holes near 1 billion solar masses existed when the universe was still under 1 billion years old. To grow that large from ordinary stellar remnant seeds, accretion must be both rapid and persistent, not just for a moment, for a substantial fraction of cosmic youth. Black holes do not simply swallow everything instantly. As gas falls inward, it heats up and radiates. That radiation pushes back. The Eddington limit is the rough point where outward radiation pressure can balance inward gravity for ionized gas. Grow too aggressively, and the black hole's own brilliance can throttle the fuel supply. That is why accretion physics matters so much here. A black hole star does not make the Eddington problem disappear. It changes where the pressure is felt. In the quasistar picture, the black hole sits inside a massive envelope. Radiation released by accretion does not escape directly into interstellar space. Much of it is trapped, redistributed, and re-emitted by the surrounding gas. From far away, the object can look cooler and larger than the violent engine hidden at its center. This is the fact worth keeping. Accretion onto a black hole can convert mass to energy far more efficiently than fusion in normal stars. A star shines by fusing nuclei. A black hole star, if it existed, would shine because infalling gas loses gravitational energy near the center, and the envelope acts as a giant converter and shield. That is why the phrase sounds contradictory. It mixes a dark object with a luminous one, and the physics says that contradiction is exactly the point. And yet, the conservative case remains strong. Many little red dots may turn out to be obscured active galactic nuclei inside small early galaxies. That explanation already uses ingredients astronomers know exist: dust, gas, accretion disks, broadline regions, patchy obscuration, and orientation effects. It also explains a practical feature of discovery science. When a new telescope opens a new wavelength window, the first surprises are often not new laws of nature. They are old phenomena seen under new conditions. There is another reason for caution. The label little red dots describes an appearance, not a physical species. It is entirely possible that several different classes of object have been grouped together because they are compact, faintly resolved, and red in infrared observations. Some may be dusty star-forming galaxies. Some may be hidden AGN. Some may hold unexpectedly heavy black holes. And if nature is generous, a tiny subset may be something more unusual. That mixed population explanation is not a compromise for its own sake. It is often how astronomy works. The night sky classifies by light. Physics classifies by cause. Those are not always the same categories. So, the burden on the black hole star hypothesis is high. It must do more than sound plausible. It must predict a subset of objects whose spectra, number counts, lifetimes, and environments fit together better than the alternatives. Until that happens, the safe reading of the Webb data is not that astronomers found one shocking answer. It is that they found a crowded crime scene. So, which future of the evidence is most plausible? Based on present research, the strongest answer is not that black hole stars were common. It is that the early universe may have used several growth channels at once. Some black holes likely began as light seeds left behind by the first massive stars. Some may have formed through heavier direct collapse pathways and rare halos, with intense inflow and suppressed cooling. Some observed red sources are probably hidden, AGN, whose masses will shrink once the modeling improves. And some of the earliest heavy seeds may have passed through a brief envelope-dominated phase that looked quasistar-like without remaining stable for long. That last possibility matters because nature often favors transient states over perfect equilibrium. A long-lived black hole star is difficult to build. A short-lived swollen accretion envelope is easier to imagine. It may survive for only a fraction of a million years, or less, before shedding mass, pulsing, or collapsing into a more exposed accretion source. If that is true, then the universe did not fill itself with black hole stars. It flirted with them. A brief stage could still change cosmic history if it produces heavy seeds efficiently. The object does not need to dominate the sky. It only needs to alter the starting conditions for the first quasars. That is the distinction that keeps this idea alive, not abundance, leverage. And that brings the investigation back to the artifact. The Ember Crown does not prove that anyone orbited a quasistar. What it does preserve is a geometry. Its veins are not burned evenly. Its calibration marks crowd into one sector. Its warning sigils map safe cones and a forbidden plane. That pattern fits a source whose danger was directional, strongest across a disk-like plane, less severe above and below it. That is not how an ordinary stellar photosphere behaves. A normal star can flare, rotate, and shed winds, but its radiation field is still broadly star-like. The Ember Crown instead implies a compact engine hidden by surrounding matter, with anisotropic output and episodic heating severe enough to force repeated recalibration. In present-day terms, that points toward accretion geometry. An accreting black hole often does not shine symmetrically. The disk, corona, winds, and reprocessing gas distribute energy unevenly. Certain approach paths are safer than others. That is true around active galactic nuclei today. It would also be true around a black hole star-like object, whose outer envelope masked a violent center. So, the artifact explains less than mythology would want, and more than fiction deserves. It does not tell us what the source was called. It does not certify a civilization. It does something better. It constrains the physics of the light source that damaged it. And that source was almost certainly not an ordinary sun. Now the informed speculation must be stated carefully. If even a small fraction of early compact red sources were quasi-star-like objects, then the Ember Crown may record a later civilization operating near one of their descendants, or near a related accretion source engineered around the same physical constraint. That does not mean anyone lived beside a newborn quasistar from cosmic dawn. Those objects, if they existed, belong to the first few 100 million years after the Big Bang. The deep future relevance is different. Their legacy would be the black holes they left behind. A heavy seed changes the entire downstream story. It can grow into an intermediate mass black hole sooner. It can anchor a dense galactic nucleus earlier. It can create an environment where reprocessed radiation, disk winds, and polar safe zones become navigational facts rather than abstract equations. So, the speculative bridge is this. If the early universe learned to build black holes fast, later civilizations may have inherited compact engines that were easier to find, harder to approach, and worth enormous effort to exploit. The Crown's shutters and flux thresholds suggest a practical response to that environment. Not worship, not mystery, but hazard management. A source with a dark center and luminous envelope is no longer just a theory in a paper. It becomes a place. That is still speculation. The evidence underneath it is not. Black holes grow. Accretion shines. Radiation is directional. Matter can hide the engine that powers the light. Those are the rails the speculation is allowed to run on. So, after all this, what has actually been explained? The opening mystery was whether some of the first red lights in the universe were not ordinary stars or galaxies at all, but black hole-powered envelopes hiding rapid growth inside. The answer, for now, is disciplined uncertainty. Established science says accreting black holes can outshine galaxies. Quasistars are a serious published model, and the early universe really does seem to contain black holes that challenge the simplest growth timelines. Active research says the little red dots are still being sorted, object by object, with no single spectral fingerprint yet decisive in every case. Informed speculation says nature may have produced brief quasi-star-like phases, not as a dominant population, but as a lever that made heavy seeds possible. And the Ember Crown, re-examined at the end, stops looking like a relic from fantasy. It looks like evidence that some later observers learned to navigate a source whose power came from concealed accretion, not ordinary starlight. The strongest competing view is still the conservative one, that dust, geometry, unresolved structure, and difficult mass estimates will explain most of what now seems anomalous. That view may yet win. So, here is the real debate. Are JWST's little red dots revealing a short-lived hidden growth machine for the first massive black holes? Or are astronomers being misled by ordinary galaxies seen through extraordinary conditions? Let me know in the comments.